This is Wilson STEM, and for my heat and power project, I chose cheap fluids in heat exchangers. So here we see the setup that I used. Fluid is forced in from the intake pot and then flows down past a T-intersection through the heat exchanger with a fan forcing air through the heat exchanger's blades, up, back through a T-intersection, and then into the waste pot. It's collected there so that it doesn't lower the input temperature. The two T-intersections have thermocouples epoxied inside of them so that the temperature of the streams is measured from within the stream itself. Measurements from the thermocouples were taken on a multimeter and then recorded as well.
Reading at 150 degrees, 151 degrees Fahrenheit and 66 degrees Celsius input. Output reading 64 degrees Celsius, 63, and 146 degrees Fahrenheit.
During the test, degradation of the seals around the pipes was evident. It was leaking both on the input and output side. Overlaid in the back is some footage showing these seals leaking. It was primarily leaking around the interface between the heat exchanger and the pipes. That is notable as it did not have any tape or sealant applied to it. It was heated and then forced into place, as well as the elbows at the top of the intake pot. This did not propagate at the top of the catch pot. The heat capacity of water was found in the back of the book in the English section. The heat capacity for salt water and antifreeze respectively were found each on a different website as linked in the sheet. The heat capacity for air, again, was found in the back of the book. Each of the heat capacities found in the book were matched up to the closest temperature. For air, since the outside temperature was 43 degrees Fahrenheit, it was used at 40 degrees Fahrenheit. For water, since it was being heated up to 150 degrees Fahrenheit, it was used at 150 degrees Fahrenheit. The density for water, salt water, and antifreeze were all found directly either from the back of the book or the website associated. For air, it was calculated down at the bottom from the gas constant, and this is assuming that it behaves like an ideal gas at this point. Pressure was recorded locally using my phone, and then from there the specific volume of the air was calculated at the bottom. For the density, it was simply inverted. The mass flow rates were calculated using the volumetric flow rate that was labeled on the pump itself, converted into imperial units, and then into the mass flow rates that we see above. The capacity flow rates were then calculated to the right using the mass flow rates and the heat capacity of the various fluids. Utilizing equation 13-10, we could use the fluid flow rates as well as the difference in temperature to then find Q dot. From here, the findings are interesting because antifreeze, despite having the lowest heat capacity and the lowest temperature in, it has the highest amount of heat transfer in BTUs per second. Meanwhile, water with the highest heat capacity has the lowest amount of heat transfer that was performed during the experiment. This contrasts with initial hypotheses of the highest heat capacity having the best performance as a fluid in a heat exchanger, given this application. Have a Merry Christmas and stay warm.